Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
So, hello and welcome to a new edition of the webinar series on AI for Earth and Sustainability Science, which is organized by members of ELIS, the European Laboratory for Learning and Intelligent Systems. Today's speaker is Hannah Meyer, a widely recognized expert in remote sensing and machine learning for the environment. She is a full professor in the Department of Landscape Ecology at the University of Münster in Germany, where she leads the Remote Sensing and Spatial Modeling Group. Hannah is trained as a geographer and was previously a researcher in the Environmental Informatics Group at University of Marburg in Germany as well, where she completed her PhD in 2018. She has projects and publications related to assessing spatial and spatial-temporal prediction models for regional and global scale, ecological and environmental dynamics. So as you can see, there could be no better speaker for today's webinar topic, remote sensing and machine learning for environmental monitoring. Hannah, the floor is yours.
Yeah. I hope you can see the slides. No, yeah. Thanks for the introduction, Alex, and thank you for inviting me to give this presentation here. And I would like to share with you some thoughts and ideas of what we might need to consider when we apply machine learning in the context of remote sensing-based monitoring of the environment. And I guess you all agree that the monitoring of the environment is getting increasingly important, for example, when we consider current topics of tree dieback that has been developed due to the drought and the bark beetle outbreak, or the increasing risk of forest fires, or ongoing aspects of land cover change with the loss of habitats that, of course, also have a consequence on the biodiversity. So the monitoring of the environment is getting increasingly relevant, but let's have a look on the fields of how we monitor the environment traditionally. So traditionally, we monitor the environment based on field surveys. For example, we might install climate stations to monitor climate variables, or soil samples or soil surveys to get information about soil properties, traditional plot-based vegetation records to get information about plant traits or species, or local animal trapping to get information about population dynamics. So what we see here are ways to monitor the environment, but when we have a look on what they have in common is that in each of these cases, these are local point observations where we get information about the environment. However, now we have a problem because for most of the questions that we're interested in spatial or spatial temporal dynamics of the environment. But now the data that we get here are only very local observations. And this is also a problem for this forest site that you can see here on the map. That is the so-called Marburg Open Forest, a research site of the University of Marburg, and also a test area for a project called Nature 4.0 that is aiming at developing a spatial and spatial temporal continuous monitoring system for ecosystem variables and biodiversity. And also here in the forest, we have the typical problem. So we have some sensors installed at different locations here in the forest, or we might go out in the field and perform expert surveys on biodiversity variables or ecosystem properties. And if we're more ambitious, we might even install sensors on board of rovers or on animals that cover larger areas of that forest But when we look on that map here, we can, still have to draw in many red question marks into that map. So these are areas where initially we don't have any ideas about the ecosystem there, simply because we never been there, we never performed any surveys, and we never installed any sensors there. So many red question marks, and this is our goal now, to fill these red question marks to get spatial continuous, but also temporal continuous information about the environment. And here, obviously, remote sensing comes into play because it provides us with information in a spatial continuous way. For example, when we need very detailed information, we might acquire data via UAVs that give us a very detailed view here on the ecosystem here from the Marburg Open Forest. Or we might install sensors on board of airplanes, for example, even LiDAR sensors, where we have the chance to get 3D information about the environment, so to get structural parameters that are also relevant drivers for biodiversity. We can leverage the long time series of different satellite missions, for example, Landsat or Sentinel, that give us continuous information about the environment. In theory, every 5 days or even more. Or if we're interested in highly temporal dynamic processes, like, for example, weather phenomena, we might use data from geostationary satellites, like here Meteosat, that gives us images like this every 15 minutes, which is, of course, very relevant when we're talking about very dynamic processes. So with these examples, we see that remote sensing provides us with spatial continuous data on the environment. But now the problem is that for now, these data are only reflectances in certain wavelengths. But we don't know anything about the ecosystem characteristics that we're interested in yet. So our key question is now, how can I translate the information that I get from the satellite or from the remote sensing system, if we extend that also to the UAVs. So how can I translate that to what I'm actually interested in from an ecological perspective? And here machine learning is increasingly used because it has a great advantage that we don't make a priori assumptions about the relationships between the variables. And this allows us to feed in a large variety of different so-called predictor variables, which might be our different remote sensing data or also other derived spatial data sets, for example, elevation and all derived variables, or also climate data. So we collect here everything that we assume might have a relationship with our target variable, so helps us in any way to explain what we sampled on the ground and what we're actually interested in from an ecological perspective. And the idea is now that we feed these predictors together with our field observations into a machine learning algorithm. And the task for that algorithm is now to learn the relationships between predictors and the response by itself. And in this way, it's possible to learn even nonlinear and arbitrary relationships between predictors and response. Based on the learned relationships, we create the model, and we can then take up the model and apply it to our remote sensing data to get spatial predictions of the environment. So here, for example, for the area around the Marburg Open Forest, the example of vegetation cover that has been modeled based on machine learning, where we see that we get a spatial continuous information about one of the variables that we're interested in from an ecological perspective. Yeah, and this workflow has in the past few years been used quite a lot to produce different environmental variables, even ambitiously on a global scale. And this slide here shows 4 of many, many more examples of where machine learning together with remote sensing and other spatial data sets has been used to produce global environmental information. For example, here, an example of plant traits, specific leaf area, or we have here biodiversity variables. These are nematodes, so little worms in the soil in 1 kilometer spatial resolution. We have global maps of soil properties. This here represents carbon in the topsoil that has been mapped based on machine learning. And this is an example that many of you might know because it has been heavily discussed after publication in Science, a global map of potential tree cover, and derived from that the global tree restoration potential. So we see here that machine learning is increasingly used to map environmental variables even on a global scale. However, what is quite interesting is to have a look into some patterns of what all these applications, or nearly all of these applications, have in common. Because when we have a look in these or in the models that are developed to produce these global predictions, that we see that the training data that are used to train these models are often heavily clustered in geographic space. So we see here the data that have been used to produce the global soil maps, the data that have been used to produce the maps of plant traits, or the maps that have been used to produce the global maps of nematodes. And we see the very typical patterns that we have some areas, like here in Central Europe, that are densely covered by training data, but there are also large areas that are not covered at all. So we make later on predictions for these areas, but initially we don't have any reference data for these locations. And this is also shown here on the right side in these figures that are showing the nearest neighbor distance distribution of our data. So for example, when we look here at the example of the plant traits, what the orange curve is showing is how far away a reference data point is from its nearest neighbor. So we see that on average, a reference or training data point is around 2, 3, 4 kilometers away from a nearest neighbor. But when we apply the model later on to make predictions for the entire land area, we apply the model to areas that are significantly further away. And this is shown here by the blue curve, where we see that on average, we need to apply the model to areas that are 1,000 kilometers away from a nearest training data point. So from a nearest training data point where the model has been learned from. So what these applications have in common is that in all of these examples, mapping requires predictions far beyond the clustered reference data. And the question is now if this is always possible to learn from highly clustered locations and make predictions for the entire land area, or if there are significant problems that we need to be aware of, and areas that are rather uncertain, where we have to be careful when we use the predictions, for example, for the purpose of subsequent modeling or planning purposes. And this is something that I would like to explore with this presentation here. And to do this, I would like to make a shift from global applications to more local applications, because the Marburg Open Forest is actually a nice example where we will later see that we can explore quite similar patterns, but because it's a small area, we can have a better track on what is actually happening here. So I would like to go with you through the example of a classic land cover classification for the Marburg Open Forest. And we see here the aerial image of that forest area, and overlaid on that, we have some training polygons where people have been out in the field and recorded the information about the tree species or some other land cover classes. And the question is now, can I use these data as training data to make predictions for the entire forest area to produce a map of land cover or tree species for the entire area based on those reference data? And indeed, also for this small area, we see exactly the same patterns as the one that we have for the global applications. So again, our reference data are heavily clustered in space, so on average here below 10 meters away from a nearest neighbor. But when we apply the model later on to make predictions for the entire image tile, we need to apply the model for areas that are 100 meters away from a nearest reference data point. So same challenge as for the global data, we see also here for that local application. So let's go into that case study. I already mentioned the task. So we want to produce a classic land cover classification. I already introduced the training data. So here these polygons of the different land cover types. And then next we need predictor variables. And as predictor variables, we use here some spectral information from an aerial image. So we have the green channel here, we have a visible vegetation index, we bring in some texture information by calculating the standard deviation in a 9x9 pixel environment based on the first principal component of the spectral data. And what we also use here is the elevation of the terrain, and we also use latitude and longitude. And I introduce latitude and longitude here, not because I really believe that they have an influence on the land cover classes for this small forest area, but I use them here because they have been often suggested by different authors to potentially improve the prediction performance of machine learning models. But I already promise that I will come back to the question whether latitude and longitude are really suitable predictors for our machine learning approach. But for now, let's just assume we take them as predictors because in theory, the machine learning model will later on handle it for us to figure out which predictors are relevant and which ones are not. So for now, we could just keep them as potential predictors, assuming that maybe they might be helpful for us to classify land cover for our forest area. Okay, so next we feed our predictors and our reference data into a machine learning algorithm. And what we used here is a random forest algorithm, because in the field of ecology, it's still one of the frequently used machine learning algorithms. Yeah, therefore we would like to stick with that for now to demonstrate the difficulties that might come up due to the clustered sampling design. So we feed in the predictors and the response into a random forest algorithm to make spatial predictions based on a trained model. Yeah, but now, of course, the question is how well can we model land cover with this approach, because technically it's not a huge problem to produce our land cover map based on the random forest model, but the question is how good is the prediction that we get out based on that approach. And to answer the question, we validated the model based on state-of-the-art procedures, and the results that we got here is an accuracy of above 0.99 and a kappa value of above 0.99. And keeping in mind that the maximum value that we could achieve both for accuracy and kappa, we could now assume that we have a perfect prediction model here, and assume we could now go on and publish these results with good conscience because we validated them with well-known procedures, and apparently we obtained quite amazing results here. However, when we have a look on how the prediction patterns actually look like, it doesn't seem to be quite that perfect. So we have here on the left side the RGB composite of the aerial image for comparison, and on the right side we see the prediction that corresponds to the accuracy and kappa of nearly 1. And I think you don't have to be familiar with that forest area to see that, yeah, this is definitely not a perfect prediction here, because we have very strange patterns. For example, this clear linear cut between predicted grassland and beech forest. We also see in the RGB composite here a forest patch that is clearly misclassified as grassland in our prediction, and also this round-shaped patch of predicted Douglas fir seems to be quite suspicious. So in summary, that doesn't look like a perfect prediction here. But the question is, how is that possible? Because the statistics just told me that I have a perfect prediction model, but now I see prediction patterns that are very obviously not perfect at all. And to understand what happened here, let's have a look on how we actually assessed the performance of our model. And therefore, we zoom in into the study area to the location of 3 of the training polygons. Here, one overlaid on cropland, one overlaid on grassland, and one overlaid on a road feature. And the way that we now assessed the prediction performance is to use cross-validation. What cross-validation in general does is to divide the data that we have available into several folds, and then models are repeatedly trained by always leaving one of the folds out, train the model on the remaining data, and then use the held back data to test the performance of the models. And the type of cross-validation that was used here is a random cross-validation. And what a random cross-validation does is to randomly divide the data into folds. So when we have a look on these 3 training polygons, a first random selection might look like this. So this means now that each pixel that is marked here with a red cross is in a first iteration not used to train the model, but is used to test the performance of the model. The same happens with a second fold, with a third fold, and so on, until each pixel that is part of the polygons is left out once and is not used to train the models, but is used to test the performance of the models. And yeah, maybe you can already guess the problem that we have here now, because by randomly dividing the data into folds, it is now most likely that in each of the fold we have data from each of the training polygons. And then it is only possible for us to answer the question how well the model performs on very similar or nearly identical locations, because we train the model on all of these pixels here and test the performance just on the neighboring pixels. So we can answer the question how well our model performs on very similar locations. But this is not what we want to know, because we want to know how well our model is able to make spatial predictions. So we want to know how well can I apply my model to the entire image tile to make spatial continuous prediction of land cover. And this is something that we cannot answer by random cross-validation if we have spatially clustered reference data, because what we actually do is shown here in that figure. So we have, again, as a red curve, the sample-to-sample distance that is showing how far away a reference data point is from its nearest neighbor. And we see in blue the cross-validation situations that we produce based on a random cross-validation. So with a random cross-validation, we're testing how well is my model able to make predictions for areas that are on average 9 to 10 meters away from a nearest reference data point. But we want to know how well is my model able to make spatial predictions, and spatial predictions in this context means we need to apply our model to areas that are around 100 meters away from a nearest reference data point. And this is something that we didn't test with this random cross-validation here. So what we need instead is a spatial cross-validation strategy where we're explicitly testing how well is my model able to make spatial predictions. So how well can it fill the gaps between my sampling locations. And one very intuitive example of a spatial cross-validation could be a spatial block approach that is shown here as a yellow grid, where we divide our study areas into smaller parts, and then we do a cross-validation again, but this time not randomly, but systematically, by always leaving one of the spatial blocks out. So for example, first training the model on all spatial blocks except for this one here, and using this spatial block to test the performance of the predictions. And we do the same with the second iteration, with the third iteration, and so on, until each spatial block is left out once to test the performance. And when we choose this spatial block approach here, we see that with this approach, we're now getting much closer to the prediction task. So we're not testing anymore how well can I make prediction for my direct neighbors, but we see here in blue that we're testing how well we're able to make predictions for areas that are further away. And in this example, we're making the prediction task even harder during cross-validation, because we're testing how well we can make predictions for areas that are further away than what is actually required to produce a land cover map for that area here. So we could assume now that by applying this spatial cross-validation, where we make the prediction situations harder, we end up with overly pessimistic estimates about the prediction performance. And to overcome that issue, we actually believe that in order to provide a measure of the map accuracy during cross-validation, what we need to do is to develop prediction situations during cross-validation that resemble those encountered while predicting the map, the global map, or in this case, the regional map from the reference data. So what we want is that the green curve and the blue curve match, so that we produce prediction situations during cross-validation that are comparable to what is actually required when I apply my model to make predictions for the entire area of interest. And to do so, we developed a new cross-validation strategy that we called nearest neighbor distance matching cross-validation, that is trying to automatically divide our data in a way that we come close to this requirement, so that the blue curve matches the green curve and that we produce prediction situations that are comparable for the prediction task. And we see the example here for two global sets of reference data, one heavily clustered data set and a randomly distributed data set. And in both of the cases, the cross-validation scenarios that we create are comparable to what is required when we apply the model to make predictions for the entire area of interest. And that this nearest neighbor distance matching approach, where we take the prediction area into account when dividing the data for validation, is indeed a good proxy for the true map accuracy, is shown here in a simulation study where we see in blue the nearest neighbor distance matching approach for different sampling designs. And we see that for regularly distributed data, for randomly distributed data, and also for strongly clustered data, we get quite close to the zero line here, which means that the estimated performance is identical to the true map accuracy. So we see that we could develop here a good compromise between overly optimistic performance estimates and overly pessimistic estimates that are probably based on the differences that the cross-validation scenarios that we produced do not match the prediction task. So coming back to the validation of our land cover map for the Marburg Open Forest, we remember we did the random cross-validation with the high accuracy and the high kappa, and now we discussed that probably the random cross-validation does not quite reflect the true map accuracy, and also the visual representation of our predictions already indicated that this is probably not really corresponding to the map accuracy. And now taking the spatial cross-validation strategy into account, so where we think about how can I divide my data so that during cross-validation the prediction situations match the prediction task, and we validate the model based on this approach, we see that the statistics change a lot. So now our accuracy drops to 0.68, and also our kappa value drops quite considerably to 0.61. So apparently our model is less able to make spatial predictions for the entire area than we would expect if we just look at the random cross-validation here. So intermediate summary, the standard validation procedures like random cross-validation may lead to an over-optimistic view on the prediction performance when we have data that are heavily clustered in geographic space, and instead prediction situations created during cross-validation should resemble those encountered while predicting the map from the reference data, so that already during cross-validation we're testing how well is my model able to fulfill the prediction task. And that this topic is still completely underestimated in the community is also reflected by the editor's comment to one of our papers where we applied spatial cross-validation that said, I'm actually surprised to see the poor performance of your neural network approach in this context here, because typically with sufficient training data, a neural network approach can often reproduce a predicted variable very well, even if the underlying reasons are unknown. But this is exactly the point that we want to make here, because to reproduce the data is not the same as making spatial predictions. And while the ability of our model can well be estimated the ability of our model to reproduce the data can well be estimated based on random cross-validation. The random cross-validation performance doesn't tell us anything about the ability of the model to make spatial predictions. And here we need to take the prediction area into account and think about spatial cross-validation, where we're really testing how well is my model able to make spatial predictions. However, we agree with the editor in one point, and this is the fact that the prediction performance is not really convincing, or the predictions are not really convincing, because we can now change the cross-validation strategy to get a better estimate about the map accuracy or the performance of the model, but changing the cross-validation strategy does not necessarily change the model itself. So we still have these weird prediction patterns in our map here. We get a better estimate about the quality of this map, but the map is still highly suspicious and definitely not what we would consider a good prediction of land cover for that forest area. So we have to find solutions on how we can improve our model to be better able to make spatial prediction here. So what can we do to improve our prediction performance? And well, the solutions are rather straightforward if we follow the XKCD recommendations of what to do in this case, which says, well, I have my machine learning model and it produces the wrong answers. So what do I do? Well, I stir around in my pile of data and shuffle things around and around until at one point they start looking all right. And for those of you who have worked with maybe small data sets, probably know that indeed, if you shuffle things around and around, you might be lucky at one point to produce something that looks reasonable to produce the patterns that you expected. But this is, of course, not the way that you want to go in order to produce scientifically meaningful results for environmental monitoring. So we should definitely search for other solutions here. And we should probably start our search by trying to identify where these weird prediction patterns actually come from. And to come closer to the answer to that question, what we can note at that point is the observation that obviously or apparently our model cannot well generalize, because we have observed based on random cross-validation that our model can well reproduce our data, but with spatial cross-validation, we have shown that the model cannot generalize, so it fails when it needs to make prediction for new areas. And the question is, why is this the case? And when we have observations like this, what should probably come to our mind is whether our model is behaving like the clever Hans. I guess that many of you know the clever Hans. For those who don't, the clever Hans was a horse that lived around 1900, and it got famous because it was apparently able to solve even complicated mathematical equations. So whenever the owner of the horse, for example, showed two numbers to the horse was able to sum up these numbers, and then he tapped his hoof as many times as needed to indicate the right answer. And this was certainly quite a sensation, but it was later found out that the horse was just reacting to some unintentional body language of the owner. So the horse has not gained any understanding of numbers or has gained any understanding of solving equation, but he was just reacting to some confounding information, to unintentional body language of the owner to produce the right answer. And as a consequence, the whole setting was not really generalizable. So as soon as someone else than the owner asked the question to the horse, so was showing the two numbers and the owner was not there, the horse was not able to provide the right answer because the information that was required for the horse to provide the right answer, so the unintentional body language, was not present, and therefore the horse was not able to provide the answers. And this is a good example of where not the skills that are required to produce the answers have been learned, but rather some confounding information, where on the first side we believe that the horse has the skills to solve equations, but only if we take really care on how do we assess whether these skills really exist, let us realize that something is missing here or something is wrong here, and the skills are not transferable beyond the training settings. And this so-called clever Hans effect also found recently recognition in the context of deep learning-based image classification. So if we stick to horses for another figure in a Nature communication publication here, the authors have been impressed by the high ability of a model to detect horses in images. So they wanted to know what is the information in this image that the model actually uses to make the right decision that this must be an image of a horse. And to answer that question, they looked into the heat map here that is showing which parts of the image are most relevant for the model to make the decision that this must be an image of the horse. And what's quite interesting here is that the bottom left corner significantly stands out here. And when we compare that to the image, this is a part of the image where a source tag is present. So apparently what happened here is that the model used the source tag to make the decision that this must be an image of a horse. Probably because the training data all came from a database where such a source tag was present, and for the model it was much easier to recognize, well, there is a source tag, the source tag also looks like that, so this must be an image of a horse. And this is also, again, a nice example where the true relationships have not been learned, so the model didn't even look at the horse, but it was learning from some confounding information, and as a consequence, such a model would not be transferable. So as soon as we remove the source tag from the image and the source tag is not there anymore, what happens? Well, the relevant information is missing, and as a consequence, this image could not be correctly classified as an image of a horse, but as something else. So what we see here is a model that is not able to learn the scientifically meaningful relationships, but where confounding information has been used to produce the answers, and as a consequence, this model would not be transferable beyond the setting and would fail in making reliable predictions beyond the cases of the training data. The question is, what does this mean for our case study now? So we have our Marburg Open Forest. We're not really happy with our predictions, and now we learned about the clever Hans clever Hans effect, and now we could assume that some of our predictor variables might act as so-called clever Hans predictors, which means they just bring in confounding informations, but they prevent a good spatial prediction because the model could not be enabled to learn about the relationships required to make predictions beyond the reference data. And what's interesting when we look into the variable importance of our model is that the top ranked variables are longitude, latitude, and elevation. So these are the variables that are mainly responsible for the prediction patterns that we have seen, and especially longitude and latitude, but also elevation are all variables that feature a very high spatial autocorrelation, where we might, as a consequence, therefore have the assumption that these variables, due to the high spatial autocorrelation, lead to the fact that they rather act as clever Hans predictors and cannot interpret it by the model in a meaningful way. But if this is the case, well, then the solution should be rather straightforward. So if we remove those variables from the model, this should, in theory, improve the prediction performance. Because when we remove the clever Hans predictors, the model should focus on the relevant predictors and should be able to learn from the relevant information. So to automatically test for that, what we did is to implement a spatial variable selection strategy into our R package cast that is automatically testing which of these variables can be interpreted by the model in a meaningful way and which ones might be even counterproductive because they act as clever hunt predictors or have no spatial meaning at all. And when we apply the spatial variable selection strategy, we see here the variables that have been selected, and we don't have to go into detail, but what's obvious is when we look at the variables that neither latitude nor longitude nor elevation occur here anymore. So apparently they have been rated as either having no spatial meaning or as being counterproductive because they just bring in confounding information into the model. And if we now limit our model to the variables that have been selected based on that strategy, we see that the prediction patterns change quite a lot. So we got rid of that clear linear cut that could be clearly traced back to a misinterpretation of longitude in the model, and also that round-shaped patch of predicted Douglas fir is not there anymore, which could be traced back to a misinterpretation of elevation in the model. So what we have learned so far is that cross-validation strategy affect the performance estimates, the selected hyperparameters. We didn't go into detail for that now, but we have seen that it affects the variable selection because we need spatial cross-validation to select the variables that can be interpreted in a meaningful way. And if we ignore that, the consequence might be unreliable performance estimates and models that can reproduce but not necessarily predict. And therefore, as a consequence, we need cross-validation strategies that fit the prediction task for model selection and validation. But the question is if this is always sufficient for reliable mapping, because what we did so far is to train and test our model based on the field observations. But again, when we have a look into the distribution of the field observations, we see that they are not evenly distributed. And when we apply our model to make spatial predictions, we apply it to areas that are far away from our reference data. And by making predictions for these areas, what we do is to transfer the model to new space, and we assume that the relationships that have been learned based on the model still apply for these new locations. However, these new locations might considerably differ in their environmental properties from our training data, and this leads to the question, what happens if the algorithm has never seen such environmental properties? And this is a problem insofar as most machine learning models are very well able to deal with complex and nonlinear relationships between predictor and response, but at the same time, they're very weak in extrapolations. So as soon as we have gaps here in the predictor space where we don't have any support of training data, we see that the predictions become highly unreliable or might become highly unreliable because the model was not enabled to learn about the relationships in these parts of the predictor space. So what we therefore need to account for that is a measure for unknown space. So we want to know which are the areas where our model was enabled to learn about relationships, and where do we make predictions for environment where our model was never able to learn about because simply no reference data were present in those environments. And to account for that, we developed a new method that we call the area of applicability, that in short is based on distances in a predictor space. So what we do is to estimate for a new data point whether this environment is known to the model or not. And to do that, we look at a dissimilarity index that is based on distances in a predictor space. So we assess for a new data point, how far away is this data point to a nearest training data point that has been used to train the model. So we developed the area of applicability based on that we define as the area to which the model can be applied because it has been enabled to learn about relationships, and where, as a consequence, the estimated performance hold. And for the Marburg Open Forest, this might look like that. So we have a Sentinel-2 satellite scene here. We have some reference data. They come here from different example of leaf area index measurements. And technically, again, we feed that into random forest algorithm, and we can technically make predictions for the entire area. But the question is, should we have done so or not? And to answer the question, we calculate the dissimilarity in the predictor space. And based on this threshold, we can then define the area of applicability, where here, as a consequence, we come up with a solution that everything that is shown in gray here features predictor properties that are very different from the training data, which is obvious because we only had training data in forest areas. So therefore, settlements or agricultural site should definitely not be part of the prediction. And these are masked here as outside of the area of applicability because we didn't enable our model to learn about relationships here. However, a question that we could also ask in that context is whether a single data point in an environment is sufficient to define that this area is inside the area of applicability, or whether data point densities should be considered here. Because of course it makes a difference whether we have one single data point in an environment, for example in a tropical forest, and our predictions are based on one single data point that has been similar to this environment, or whether we are located in an environment that is densely covered by reference data, where we had multiple data, where the model was enabled to learn about relationships. And therefore, as a add-on to the area of applicability, we suggested a method of calculating local data point densities that again shown here for the Marburg Open Forest. We have here the training data of the leaf area index again, and we have here the local data point densities that is showing how many data points were in the training data that are similar in their predictor space to a certain environment. So everything that is yellow here are areas where we had many data points, so 30 in this case, that featured similar properties compared to this environment. And therefore, we could think about whether this model is rather certain in this environment because predictions are based on several training data points, while areas that are shown in dark color here don't have much support or even no support by training data, and should therefore be regarded as rather uncertain. We could even go further and think about whether we could use that information to estimate the prediction performance, where we use the local point density here to assess the relationship between local point density and the root mean square error based on cross-validation, where we see here with increasing local point density, so the more data support I have, the lower the root mean square error. And if I use that to make predictions about the root mean square error for that forest area, we see here the estimated root mean square error with areas with high error that had little support by training data, and areas in darkish colors are those where we had many data points, so the model was enabled to learn about this environment based on many reference data points. So why is that important to come to a conclusion? Well, the results that we are producing based on remote sensing and machine learning are not just nice maps, but we use them as an input for to support modeling, conservation and risk assessment, and for subsequent scientific purposes. And therefore they have a high relevance to support the sustainability goal number 15 and also beyond that. And I think that we as the producers of the maps are responsible to clearly communicate the usage of the maps, and that we should probably not leave the interpretation to the user, because at least me as a user of data and also knowing my colleagues, we tend to not go too much into depth about assessing the communicated or the additional uncertainty layers that come with data products. And therefore, I think that we as the producers of the maps should be very careful to clearly communicate the usage. And I think that we need to convey the model's predictive capabilities and acknowledge its limitation, for example, by clearly marking areas that are outside of the model's applicability. And finally, I think that identifying such gaps isn't really a flaw, but rather we should see that as an opportunity to refine and improve future models so that we can move forward towards more comprehensive monitoring of the environments by identifying areas where more support is currently needed. And yeah, I hope that maybe this talk initiates some discussions on how we can continue to come closer to that aim. And with that, I'd like to thank you for your interest on that topic.
Okay, thank you very much, Hannah, for this very inspiring talk. And so I will be taking questions from the audience. Haven't seen any so far, but in the meantime, so please take your time to write your comments and questions, and I'll be happy to convey them to Hannah. But in the meantime, I'd also have a question myself. And Hannah, I see that you're, at least for me, you're frozen, but I hope that's not a problem on my end.
No.
Okay, I see. Great.
Don't know what happened.
So, yeah, so your focus was on assessing the model performance in spatial dimension and in feature space, but you also briefly mentioned interpretability of the final maps through the lens of model performance. You also showed some variable importance graphs of your, I think it was a random forest model. So in this context, what is the importance of model interpretability? And so, I mean, you showed some examples of model interpretation. I guess that was the permutation method. There are other methods out there, like the SHAP values. Are these methods currently sufficient to explain the behavior of black box models to users and to decision makers who want to trust those models, who want to understand that the models are actually coherent and consistent with the processes that they know so well?
Yeah, so I think that certainly simply the importance scores that I have shown are not enough to really communicate the relationships, because it can just give the information, well, elevation is important for my response variable. But of course, everyone wants to know, but how, or maybe elevation is not a good example, maybe something where we can really something do about, for example, management strategies. I want to know, what do I need to change in order to reach a certain goal, and just knowing, well, this variable is important is certainly not enough in this context. I think maybe it's less important if we stick to pure remote sensing data, where our question is, how can I predict my response variable based on the spectral information, because there it's less important to get the exact information on how the different spectral channels relate to my response. But as soon as we use variables like climate variables, we use more information that describe the habitat of for example, species, or also management strategies, and use them as predictors. Of course, we want to know how do they interact, and how are they, or what is learned in the model to make certain predictions, and what would I need to change in order to also change my predictions. And as soon as really the interpretation and the understanding of the system is at least equally important, then just the importance scores are certainly not enough. And Shapley values at least already give us more the information about how the relationships between the predictor variables look like.
Okay. But would you say that Shapley-based explanations are sufficient to explain to maybe an affected person who in a hazard zonation as a result of a hazard assessment will not be allowed to build on their property? Are those methods sufficient to explain the model's behavior and plausibility? Or do you think that's an area where there's still a lot to do, or where specific models could be more useful than black box models such as random forest?
Oh yeah, probably, definitely, yes, yeah. So I didn't study those methods myself, so I don't feel fully qualified to give an answer about that yet. But we definitely also have to be very careful whether the relationships learned by the models are really causal relationships, or if there are no like with the clever Hans effect, relationships that have been learned that are not really transferable, so that whatever action I take does not really have an effect on my outcome later on, because the model has just learned from confounding information. And this is something that can definitely not explained by the Shapley values. And with this, we definitely have to be very careful. But it could help us to draw hypotheses that could be tested also with other approaches. And I think for this, that already provides quite interesting information.
Okay. We have one question from the audience, which is, would data augmentation, oh no, sorry, how would data augmentation influence this problem?
Yeah, I heard that question several times, and I'm not fully sure how we can apply data augmentations for examples like that. So I know that, of course, from CNNs, from image classifications, where, of course, the model should also be able to detect tree species if I flip the image, if I change the brightness of the image, and so on. But here, what should I do? Because the predictors like elevation, climate, the remote sensing predictors, these should represent the true values. And how should I change them to increase my amount of data? Because I just make it more uncertain, I think. So I don't see a way, and I'm still hoping that someone provides a good answer to that question, because I heard that many times. So far, I'm not convinced about how this could be helpful in this specific case. So definitely not for image detection, like with a horse image. Of course, a horse should also be detectable as a horse if I flip it around, but I'm not sure how I could do that based on my local field observations.
Okay, but I guess the point is that it can mitigate overfitting. So I think in your application context, it would entail wiggling, for example, the coordinates, for example, some feature values, under the assumption that in the real world, this would not change the predicted value, the class membership, etc.
Maybe
it should not, and that, especially in the case maybe of strongly overfitting methods like random forest, might help mitigate those, sometimes you get spikes in the predictor response.
Yeah, true.
So
but
okay.
maybe depending on the degree of clusterness, we would need to wiggle them quite a lot. And then the question is, do they still represent the true values that we want our model to learn from?
Right. Yeah. Okay, good. Thanks for that question. Then next one is, how can we explore alternatives to determine when the number of samples and samples per class are sufficient? So sampling design, can this help determine a sample size per class in total?
I'm not so sure about the sample size, but at least already in terms of design, I think it would be quite helpful to look on the applicability of the model, for example, with the area of applicability or different approaches, because that would already help me to identify where based on my sampling design, I'm not able to make any predictions. And as a consequence, that would be helpful to also target upcoming field campaigns and to subsequently fill the data that are required to make predictions, so that I'm not maybe unnecessarily increasing my amount of data in areas where I already have quite many training data available, but look specifically for those areas where I have very few support of training data, so that I could strengthen my model in order to make also predictions for those locations.
Okay, good point. So basically being aware of the issue of area of applicability also already paves the way towards more targeted sampling or identifying gaps in sampling designs, right? So yeah, okay. Then there's another question that came in, which concerns the performance measures that you used. So you focused on the kappa index and overall accuracy in the model assessment. So what about the F1 score, which balances precision and recall? I guess there's also other ways of accounting for the differences in the cost of misclassification of false positives, false negatives. Any thoughts, any comments on that?
Totally agree. So I totally agree on that. The reason why we used accuracy and kappa was that we did that study to really make the point of what can happen here. And then accuracy is very easy to interpret and to show the effect of what is happening if we change certain strategies. But I totally agree that accuracy and kappa, especially if I have unbalanced data, might not be ideal performance measures in this context. But I believe that the view on the performance measures would not change. So still the difference between the random and the spatial cross-validation would be comparable if I use more appropriate or different performance measures, because it's so obvious and such a clear and strong pattern that I'm quite certain that also with different performance measures, the pattern would be the same. But here it was really used to make the point clear. So we're focusing on these rather simple measures.
Right, yeah, and I mean, that relates very much to one of the points in your conclusion, which is to take a user-centered perspective, which means pick a performance measure that matches the user's needs and not the producer's needs, right?
Mm-hmm.
So even for the same prediction problem, different performance measures may be relevant depending on the target audience and application.
Yeah.
One more question came in. You focus on spatial prediction, but some of your research is also spatial temporal. So the question is, can this method of area of applicability also be used for forecasting tasks, or maybe more broadly for time series prediction, like hindcasting, right?
Yeah. So actually, so the term area of applicability often suggests geographic area, but it is not. So it could be applied to a completely non-spatial and non-temporal data, but then of course also to temporal data, because we see the area as a domain where we can apply our model, and this could be temporally as well. So you could apply it in the same way to spatial data or even to spatial temporal data. That shouldn't make a difference in terms of applicability, technical applicability.
Yeah, okay. And I think looking at the time as well, I think this is a very good question and outlook also towards from spatial prediction towards spatial temporal. And let's see what the future brings. I think Hannah also presented several directions that can be followed up on in the future. So thank you so much, Hannah, for providing those insights, for inspiring us with the methods that you propose and that are implemented in the CAST package in R. So with this, I would like to close this session. Thank you, Hannah. Thanks to the audience for contributing, and see you next time.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
you.